All right, this is the last lesson in the series on thermodynamics with heat and temperature. We have the next section that we use heat in, especially when we get to looking at absolute temperatures. We will do that when we get to the section on fluid dynamics because the two of them are so interrelated. We know temperature affects pressure. Pressure can also affect temperature. So that'll be our last section, but you're going to do a test on this section first. And just to wrap it up, it makes it a little easier, especially when we're doing everything by distance, and it can get confusing when things get muddled. All right, so for this section, we're going to first review the last lesson. So I want to talk to you about sensible heat. I want to talk to you about latent heat and just give you a reminder of how it works. And we're going to do one of the combination problems because those are the hardest problems to identify. Now, I've just misplaced my pen here. So just give me a second and we'll find that. All right, I've got my pen for my tablet here, so we're able to do some math again. So first of all, sensible heat is heat that results in a temperature change. Sensible heat uses the formula delta H equals MC delta T. So delta H just means the change in heat. This is a change, is equal to mass times the specific heat capacity. This number again is from your chart, times the change in temperature. Latent heat is heat that results from a change in phase, so melting or vaporizing. Okay, so if we think about that, that would be like if a question says ice melts. As soon as you see the word melts, that tells you have latent heat. If it says ice melts and temperature changes, then we know we have a sensible heat question as well in there. So we've got two things happening. So we watch for those keywords about something melting or water being turned to vapor or to steam. That would be vaporizing. So that's going to be another clue for us. Now, the formula for latent heat is just mass times the latent heat coefficient. Now this L comes from our chart. There's going to be two different L's for most things. That's going to be one of the L's will be for something vaporizing or going to a gas. And the other one will be for something solidifying, crystallizing, or going to a solid. So it takes energy. And if you want to prove that it takes energy for crystals to form or for crystals to be broke up, now here's an example you could try. Take a cup of water, just room temperature, dump a huge pile of salt in it, and just put your hands around the cup and feel what happens. We can tell that it takes energy to break apart those crystals and to dissolve the salt that's there because you'll feel that cup will get cold. It works best if you have a glass cup. And that would be very, very similar to latent heat. That's not exactly melting, but it kind of gives you that idea of what's happening in different processes requiring energy. That was a common experiment that we did as proof in our chemistry classes. It's much, but we all know in order to melt ice, we have to apply heat to it. We have to have a warmer room. So that in itself should be evidence enough for us that the melting process requires energy. Latent heat and sensible heat might both be needed to solve a problem. In that case, we're going to look for temperature change and phase change. So I'm going to do one review question with you, and then I'm going to talk briefly about thermal equilibrium, and that will have us wrapped up this section. So here's an example question from the sensible heat and latent heat calculations. I'm quite certain that this question is word for word in your practice worksheets. So if you're working through some of them, or if you want to give it a try on your own, download the worksheet and do those worksheet questions for practice. So let's look at the question first. We're reading the question, and as we read the question, we want to ask, is this a sensible heat question, or is it a latent heat question, or are both of them working together, and how do we know? Let's read it carefully first, then we'll go back and we're going to look for the information. How many calories of heat are needed to melt 325 grams of ice at 0 degrees Celsius and raise the temperature of the melted ice to 335 degrees Celsius? So let's look for the important information to decide what kind of question. Well, there was a couple key things that I noticed as I went through. The first thing I noticed was it asked for calories. That's going to be important to me regardless of which one I'm solving. So I'm looking for all of my units. I'm going to use calories. How many calories appear needed to melt? As soon as I see melt, I know that we have latent heat. Okay? And this is going to be fusion. Okay? Think about fusing and freezing. They both start with F. Melting is the opposite of freezing, so that still uses fusion. Okay? So freezing or melting are going to use the same L value. It's just a matter of whether heat's given off or whether heat's absorbed. And we won't worry about the specifics on that for your short course. Okay, so now we know we have latent heat in this question, so there's fusion, but we have to keep going. So it says the ice is at 0. This word here is a big clue for us, and. We've got probably a combination. And raise the temperature. This word raise the temperature tells me that there is sensible heat involved, okay? Of the melted ice to 35 degrees. Now, melted ice is also known as water. So we're going to have to watch. Once we're at a temperature that's 0 degrees or above, we're going to end up switching our values, or above 0 degrees, we're going to have to end up switching our values and using water instead of the values for ice. So let's look through and we're going to work at this question. So we have sensible heat and we have latent heat. Let's look at what formulas we're going to need to use. So first I need to find out what is the delta H to melt. Okay, and the formula for that, for latent heat, is delta H equals M times L of fusion, which means we're going to have to find some information. So first of all, we have a mass of 325 grams. L is in our chart. So let's look up the L. Remember, we want to use calories and grams. So I put it in the next slide if you happen to have them printed off, or if you have the PowerPoint and you're working with that. So we have ice, we're melting ice. So the first thing we're going to do is find ice on our table. So here's ice. And let's see how straight I can draw the line. All right, there's all our values for ice that are boxed. Okay. So we are looking for the heat of fusion. So we're in this part of the chart for ice. We want calories and grams. So we're going to look in this column. So the heat of fusion, this is our L, is going to be 80. If it was steam, we would be over in this section. But we have ice and we have 80 for our heat of fusion. So let's go put that in. So 80 calories per gram. Now we can calculate. So the change in heat is equal to 325 grams times 80 calories per gram gives us a total of 26,000 calories. Okay. A little hard to explain that in calories, but this is technically, for those of you that have been lounging around on the couch too much during this period of isolation, if you want a low effort weight loss plan, there is proof that eating ice chips helps burn calories because it requires energy from your body to melt them. I really wish somebody would develop some kind of a diet plan that just involved drinking cold water and eating lots of ice, because it sounds like a lot less work than trying to do some kind of home gym workout. If any of you try it, let me know what the success rate's like. All right, so we just have the first part of the question, okay? So delta H to melt our ice. That's part one. Part two, well, our ice is melted now, and we want to know, so ice is melted to water. Okay, So now that the ice is melted to water, we need to find out, well, how much heat was required to change the temperature of the ice from 0, or the water from 0, because it was 0 right after it melted, up to 35 degrees. So we're back to mc delta T. This is our sensible heat. Okay, so that's the second step, is sensible. Let's plug our values in. So again, I'm going to pull the information out here on the side and then we'll calculate. So we have the same mass. The same mass of ice was just converted to a mass of water. So 325 grams. C happens to be on our chart, and let's go look for that C. Remember, our ice is now water because it melted. So now that the ice has melted, we won't use this value anymore. We're going to be down here. Water, because it's liquid. And these are the values for water. All right. So sensible heat uses the specific heat. So there's our C value. We want calories in grams. So we're going to look all the way down our chart here, and we're going to take this value. We're going to take 1 calorie per gram. So, oops, I keep wanting to go to the next slide instead of backwards to the old one. So we have 1 calorie per gram per degree Celsius. Our change in temperature is equal to 35 minus 0, which is 35 degrees Celsius. So now we can put all of that into our formula. So heat is equal to 325 grams times 1 calorie per gram degree Celsius times 35 degrees Celsius. Combining all that together in our calculator, we find we have 12,250 calories of heat. To finish off the question, it's an and question, so that means we add the two components together. So the total energy is equal to 26,000 plus 12,250 equals 38,250 calories. And that's the final answer. So a lot of little steps for those questions. I would recommend, if there's a question like that on the test, keep track of your work. And if you're unsure, or if when you submit it, you see you've got that question wrong, please forward your work to me. By doing that, I'll be able to award partial marks in order to help you out in getting a few extra marks. So a question like this, because it's a more complicated question, I'll typically assign it a 3-point value, so that if you send me your work, you'll get some of those 3 points. So hopefully that helped a little bit with sensible heat and latent heat, that you have a whole bunch of practice questions on them. Feel free to do the practice questions. You've also got questions in SAM. The quizzes that are built in SAM have unlimited attempts on them, so you're welcome to do them as many times as you want before you do the test. I do request that you get a 70% before you continue. The last piece we want to talk about, and we're really going to mostly talk about this, I will do one calculation with you, but you will not be expected to do a calculation like this for this unit, just simply because of the change in delivery method and the amount of time we have to go over it. Thermal equilibrium is defined as when heat travels from hot to cold until they reach the same temperature. Once two objects are at the same temperature, it is considered to be in thermal equilibrium. No more heat's being transferred. They are thermally equal, or their temperatures are equal. Now, that just simply means that the energy lost by the hot object, so this is our hot object, is equal to the energy gained by the cold object. It's actually an example of conservation of energy. Energy is neither created or destroyed, it's just transferred from one place to the other. And because it's just transferred from one place to the other, that allows us to figure out what would the final temperature of the object be. Now, again, this is if it's only changing temperature. We could include thermal equilibrium in this, like if ice was melting or something, but that actually makes the question a lot more complicated. So I'm just going to give you an easy example. I'm pretty sure the easy example you will consider to be complicated enough. Again, I will not be expecting the calculation from you. So if the heat lost by one object is gained by the other, then if we take the mass of the object, the specific heat of the object that's losing energy, and multiply it by the temperature, that should be equal to the mass of the object gaining temperature, gaining heat, the specific heat of the object that's gaining heat, and the change in temperature of the object that's gained heat. Those values will be equal, which gives us just simply this equation where TL is the temperature, the initial temperature, the hot temperature of the object that was losing heat, the object that's cooling down, minus the final temperature, which would be the equilibrium temperature. And that's going to be equal to the, over here, we're going to have the equilibrium temperature first, because it's going to be the higher value. This is gaining heat, so we put the highest temperature first, and then we subtract what the original temperature was, or the original colder temperature. So it just gives us positive values by doing it that way. All right, let's look at a slide quickly. We'll look at a picture just to review the concept. Then we're going to do a quick calculation, and that wraps us up. So let's assume that these boxes happen to be the, hopefully that music in the background isn't being picked up too bad. Anyway, I'm done with fighting with my husband for teaching time. For those of you that are living with spouses or parents or roommates, it's a challenge. All right, so we have each of these scenarios. These are just 3 phases of the thermal equilibrium. So we start out with 2 objects that are at different temperatures. Okay, this is the hotter object. The little bright circles around the edge here just showing that it's got more energy, more motion. So we have 2 objects with different temperatures. So this is our hot, and this one is cold. We bring them into contact with each other, and just by being next to each other, energy is transferred. So heat, I can't write, heat transfers from the hot object to the cold object until the temperature is the same. Of both objects. Okay? Once the temperature is the same, there is no more heat transfer, even if they're in contact with each other. Now, I saw a really interesting question that said, well, what if one object has twice as much heat as the other, but they're at the same temperature? Will energy transfer? And the answer for that would be no. Just because they have different amounts of energy doesn't mean that energy is going to continue to move if they're at the same temperature. Thermal equilibrium, or transfer of heat, is only going to happen if the temperature is different. So heat only moves, let me see what I can do here. If there's a temperature difference. Okay, so that's something that's important for us. Heat only moves if there's a temperature difference. If heat moved, regardless of whether there is a temperature difference or not, it would make for a very chaotic world. If energy was always moving, it would mean we had no control over energy moving. Because like, let me think. So for example, I'm trying to think of what we have that would be in contact that's 2 different masses. Okay, for example, my house, for example. Okay, so the house is the same temperature as the air outside. Now my house has a substantial mass. It's not transferring energy to the air that's outside because there's no difference in temperature in them. It's exactly the same. Now the sun has a massive mass, but it happens to have a lot greater temperature, and that's what allows us to transfer that energy to, you know, our atmosphere or the world around us. Anyway, I don't know if that makes sense to you. Sometimes it's harder to explain when you go try to put it into words. So I'm going to do one example question with you just to show you how the questions work. And then I'll give people just talk through a final kind of review example, and that will have us finished off. So 12 kilograms of aluminum at 465 degrees Celsius are placed in 25 kgs of water at 15 degrees Celsius. What's the final temperature at thermal equilibrium? So this question is a bit of a complicated question for us. So let's think about what's losing heat. So the aluminum loses heat. Okay, its temperature will drop, the water gains. So for this question, the delta H of aluminum has to be equal to the delta H of water. All right, so this means that MC delta T equals MC delta T. Now I'm going to put aluminum on one side, I'm going to put water on the other, and we're going to do a little calculation. So the mass of aluminum is equal to 12 kgs. Our C we're going to have to find, and our change in temperature, well, we can't really tell our change in temperature because we don't know what the end temperature is, but we know it's going to be 465 minus the final temperature. Okay, we're just going to leave that. We're actually going to do some algebra with this. All right, let's find the C for aluminum. So aluminum is here. C is the specific heat capacity, so we're in this column. And I'm going to suggest we do this in calories, and you will see why at the end. If you do it in joules, it's not going to hurt at all. So this will be kilocalories per kg degrees Celsius. So that was 0.22 kcal per kg degree Celsius. So we have all the information for this side of the equation. So it's going to be 12 times our C of 0.22 times our temperature change. And we're going to do that in brackets because we couldn't calculate it. So 465 minus TF equals. Now on this side, let's list our variables for the water. So the mass of water is 25 kgs. C, let's go back and find out what it is. Oops, let's go back and find out what it is. So the C for water, water's down here. And the C value for water, take everything from the same column, happens to be 1. You can probably see why I chose water or why I chose calories to work with instead of joules. And I did it just because I know that the specific heat of water is 1 if we're in kilocalories. So we'll go back and we'll put that into our equation. Okay. Cal per kilogram degrees Celsius. And our change in temperature, well, the temperature increases. So the hot temperature is going to be the equilibrium temperature or the final temperature. And the colder temperature that we're subtracting from it is our 15 degrees Celsius. Okay, so let's plug that into our equation down here. 25 times 1 times TF minus 15. So this equation looks really ugly. It should take us back to when we did some algebra. So we're just going to simplify it, and I'll show you how I simplify it, and then it's actually not that bad. So 12 times 0.22, let's combine these first. That's going to give us 2.64, and we're going to leave what's in the brackets. Equals 25 times 1 is just 25 TF minus 15. All right, then what we have to do is we have to do this like expanding, okay? Distribution. So we're going to multiply the 0.25 by both terms. We're going to expand it to get rid of our brackets. So 2.64 times 4.65, 465. Let me just go and edit here. I had a dyslexic moment, which is not unusual for me. You know me well enough at this point. 465. All right. So 2.64 times 465 leaves us with 1,227.6 minus 0.264 minus times TF, which just gives us 2.64 TF, equals 25 times TF minus 25 times 15 leaves us with 375. And now we're just to rearranging. We're going to combine our like terms. So the two terms with TF, they're the same kind of terms. We'll combine them. And the two terms that are numbers, we're going to combine. So let's put the TFs together. So I'm going to move this to the other side by adding it. And that leaves me with 27.64 TF. So 25 TFs plus 2.64 TFs leaves me with 27.64. And then we'll take our 375 and we're going to move it. So in order to move it to the other side that has just numbers, so we put the TF on this side. So all of the numbers without a TF, we're going to go to the other side, add 375 to both sides. And on this side, so that's gone to 0, that's gone to 0. And on the other side here, we're left with 1602.6. The final step, you guys are quite familiar with rearranging. You divide by 27.64. And the final temperature is equal to 58 degrees Celsius. So we find that the water doesn't change its temperature nearly as much as the aluminum. Then that's partially because it has a much greater coefficient, specific heat coefficient than what aluminum does. And that's one of the reasons why we use reservoirs, and we have things like engine coolant has a fair bit of water in it, because that water can store a lot of energy. Its temperature doesn't change a lot, but it does a lot of work to cool down that metal and to basically save parts from failing. So thermal equilibrium is something you use in your trades. It's the whole principle behind how rads work. Sometimes we want to use it to cool things down. There's other times we want to use it to heat things up. And when we're heating things up, we're thinking about baseboard heaters, hot water baseboard heaters, which are much more common at PEI than they are in some other places of the Maritimes, in order to transfer heat from my hot water tank to the environment. So thermal equilibrium is actually a very important concept around us. And this time of year, as the sun comes closer, we feel more energy from the sun. We're extremely thankful for that heat transfer that's making things feel a little bit more like spring out there. All right. Now I'm going to just quickly tell you about this. This is something that I would have liked to have done if we were in a classroom setting, but we're not. So a calorimeter is just a tool that's used to measure the heat transfer. So what you do is you fill it with water, and you measure your temperature of the water that you put in, and then you put hot metal in it, or it might be, we used to actually do chemistry reactions in them. We had bomb calorimeters, and the bomb calorimeter, you would actually heat materials up until they completely combusted to figure out how much energy that material held. It was cooler than it sounds, and yes, that is where I get a little bit nerdy. It was also in a course that I thought was going to kill me, but I did really enjoy the lab components of figuring out how does energy transfer. So you put it in a highly insulated material cup. I have a few not highly insulated ones, but ones that work close enough. And then you would combine your two materials and you find out when it gets to the equilibrium temperature, that allows you to figure out, well, what is the specific heat? And if you're wondering how they come up with the values that are in the charts, the values that are in the charts, they came up with them using tools like a calorimeter. Anyway, calorimeters are actually pretty cool. You can do some digging and investigating on how calorimeters work if you are interested in it. But if you were doing any kind of chemistry or thermal chemistry, this would be something that would be quite important to you. Now, one thing I do think about when I think about a calorimeter, we have a really, really, really insulated container in order to prevent heat being transferred to the outside. And this is not at all unlike highly efficient hot water heaters. A really efficient hot water heater is going to have a high amount of insulation just to prevent the heat from that water being transferred to the environment nearby when I don't want it to be transferred. Okay, so when it's not coming out of the shower head or in my dishwasher or the washing machine or a situation like that. It's also one of the reasons why it's recommended that you put the lovely styrofoam covers on top of your hot water lines, is just to prevent energy transfer so that you maintain or you hold as much of that energy as possible in the water rather than transferring it to the environment and basically wasting energy because your water is not as hot coming to your taps. This is an example where I've had other years, I've actually had the class build a little hot water heater, and I really, really like this example. It kind of gives us a quick overview of this section. So I want you to think about, well, where does radiation occur? Well, radiation occurs when the sun shines down on my solar hot water heater, okay? So the sun shines down on solar roof collectors, and there is water going through channels in this solar roof collector. So the water is going through here, the sun radiates on it and transfers energy to that cooler water, okay? And now here it says there's antifreeze in that water, which makes sense because especially if we're doing it in a northern climate, we want to make sure that we're not going to have any freezing happening because that's going to be relatively dangerous. All right, so the water is allowed to come in. It circulates through the solar panel on the roof where radiation happens. So radiation happens on the roof. That water then transfers into a holding tank. So this is my solar tank. This is where my hot water sits. And here I have hot water in it. Notice that water is not going through the coils, okay? The hot water going through the coils heats up my metal, which heats up the water in this tank. So in here, we have conduction happening in the coils, okay? So water is heating the metal from the coils, which is then heating the hot water around the outside of the tank. Where does convection happen? Well, convection happens in the tank. Heat rises, you'll see up here, the brighter red is an example of the hotter water, where the more orangey color is our cooler water. So convection happens in the tank as well. Okay, and where does thermal equilibrium occur? Well, thermal equilibrium happens inside, well, we're aiming for thermal equilibrium to happen inside of our tanks. We want both tanks to end up being exactly the same temperature or close to the same temperature. So the warm water coming in heats up the cool water. It may never quite reach thermal equilibrium because this is a system that's always changing, but if it was allowed to sit long enough, the water would end up coming to thermal equilibrium. Now you'll see that here we're connected to a boiler, and basically what you're doing is we're using a solar roof collector is being used to boost the energy that the boiler provides. So it lets the boiler work less hard, so less energy is consumed in oil because the water is basically coming in preheated. And by preheating the water, that allows me to, by preheating this water, the boiler doesn't have to work as much. It's just basically acting as a backup for us. Anyway, I don't know if you actually discussed solar hot water heaters in any of your classes, but I thought it was kind of neat, and it actually makes us think about all of the components of heat transfer and why heat transfer matters. Now, that's all I'm going to cover for this section. While you wait for me to get that test live online, I would suggest that you think about, well, where does radiation, conduction, convection, and thermal equilibrium occur in your trade? That means even if you're one of the wind techs, or if you're in the gas turbine class, you're going to find that you have radiators somewhere. Think about how that relates to radiation, conduction, convection. Something to think about is what colors absorb the most radiant heat. What color do we paint things like windmills? How many black ones are out there? Is there possibly a reason for that? Why do you think that could be an issue? If you want to think of construction, let's think about our roof, solar panels. What color are they? Okay, a roof, black shingles degrade faster than light colored shingles. How would that relate to thermodynamics, and what would that possibly mean for my attic? So there's just a couple questions for you to think about, some examples for you to possibly draw from without me giving you all the details for them.